Thank you, Silvio. So it's a real pleasure to be here. I only knew Cyrano after I came to this lab about 8 years ago. So I enjoyed his company in his late days in the lab. Didn't work with him, but what I know is that he loved spin glasses, and I hope that he would enjoy to hear about where all the things that we learned in spin glasses are being used nowadays out of the field of physics. And with this in mind, I prepared this talk. And also to be able to concentrate more on the concepts, I will most of the talk concentrate on a model that I think most of you are familiar with, the perceptron. And this way we will, that's the familiar part, and somehow the new parts that I want to stress should pop out of it. So the motivation, and okay, so it's a work that, whole project that we are working on with Florent Xakala, and also with collaboration with Marc Mézard, later with Nicolas Macris, and then the names in white, that's our students and postdocs that joined that effort in the past years. So what's learning a rule? What was this about? So imagine that I give you a set of photos of cats and dogs, and your goal is to stare at them for a while, and then to be able to tell which photo is a cat and which photo is a dog. So of course, my little daughters are able to do that, so that doesn't look very difficult. But think about it from this point of view of a computer that does that. So how does a computer see this photo of a dog? It's some vector, right? Every pixel is stored its color, so this would be the red, blue, green, etc. And then so every color of every pixel is this 8-bit zeros and one number, and you just go, and you have several megabytes of numbers like that, and this is an input into a function that should output 1 if it is a cat and -1 if it is a dog, and your goal is to find this mathematical function f. Okay, so stated like that, it looks less trivial, because how in this mess of 0 and 1s are you supposed to know if it is a cat or a dog? So this is a very challenging problem. Nevertheless, today, this can actually be done with computer, with something that is called convolutional deep neural networks, which is something that appeared in the, say, last 10 years. And it's causing amazing excitement in pretty much every area of science, technology, business. It's artificial intelligence. The promises are huge, the stakes are huge, etc. So that's somehow the motivating fact, the motivation to look back into what in statistical physics we can say about a problem like that. And fortunately for us, we actually have a model for learning a rule. So if you go to Google and type statistical physics of learning a rule, one of the papers you will bump into is this paper by Bernard Derrida and Elizabeth Gardner, where they study several models. And there is a model B in that paper, and that's the one that I'm defining here. So how does that work? So F will be the data. So it's a matrix with two indices. The index mu will be indexing different pictures, different samples. The index I, that would be the dimension. That would be the number of pixels in every picture in the analogy. But in this model, we will be taking the matrix F to be IID with 0 mean and variance 1 over n. So every element of this matrix is just a random number. And then we generate a vector x star. So you can imagine this matrix. So if we were in 2 dimensions and had 22 points, these points would be the rows or columns, I never know, of the matrix. And then we generate a vector of a dimension n, which here is coordinates of a hyperplane in this space. So here is just a line, but we are in high dimensional space eventually. And then the labels are generated like this. So the x star is multiplied by this matrix F, and the labels, so if somebody is green, cat, or red, dog, is this y. Okay? And then the goal in this model is that you're given the matrix F, and you're given the labels y, but you're not given the x star. It comes from some distribution, and you're given that distribution. Okay, I'm nice to you. But you're not given the vector x star. And the goal is to infer the X star from the set of examples F mu and Y mu. And so that's one important question. Can we learn back that X star? And in classification problems, in these problems of cat and dog, there is the important concept is that if I give you a new picture that you haven't seen previously, that your function should be able to tell if it is a cat or a dog. And this is something called generalization in machine learning or in the theory of neural networks. And in our example, this ends up if I now generate a new row of this matrix, which would be, for instance, this point, did you learn the X star well enough so that you can tell that this point is red or green, right? So in this example, by the way I draw it, it must be red with very high probability. So that's the concept of a generalization error. So what's the probability that you are labeling new points correctly? Okay, so that's the problem, the MAL. So on a side note, this MAL, I will call it the teacher-student perceptron. On a side note, the original paper of Gardner and Derrida and many other papers, and also yesterday in Imre Kondor's talk, and I think also tomorrow in Giorgio Parisi's talk, there is a similar MAL but with a different question, the question of storage capacity, where you also generate a random matrix, but in storage capacity you generate a random vector y, and you're asking if there is an x so that these things are satisfied. Okay, whereas here I have this X star that generates Y, and then I'm trying to find the X star back. And these are two different problems. This one is also interesting, but note that in the storage capacity there is no notion of this generalization error. If I give you a new row, then the new Y is random, and there is no way you can predict the random number. Okay, so this concept of generalization error that we care about the most in machine learning and neural networks is not there if we generate the Y randomly. So that's why I focus on this teacher-student scenario where there is some ground truth that I am finding back, and if I manage to find it back, I can define what's the generalization error. And that's something that has been done in these old papers. There will be a paper just 1 year after Gardner and Derrida by Geza Georgi, who studies this generalization in the MAL as I defined it, with this X star being just a binary number, so Ising spins if you want. And interestingly, he plots the generalization error computing from the replica method in the limit where the dimensionality of the data and the number of samples is a fixed ratio alpha. And in the whole talk, that will be this fixed ratio alpha. So he plots the generalization error, that is something big and uninteresting, that suddenly drops to 0 at a phase transition that happens at alpha that is 1.245. Okay, so there is a first order transition to perfect generalization. He suddenly managed, so the optimal method learns the X star perfectly, starting from this alpha. And then actually this curve continues. There is this dashed part of the curve. That's a picture from this paper. And he says this dashed part line represents the non-physical segments of the curves. And doesn't comment more on it. So keep it in mind, because that's somehow our point towards the end. At the same year, actually the same phase transition, I think independently at that time, was found by Sompolinsky, Tishby, and Sung at the same place, fortunately. But they also say, something interesting. They don't have this unphysical branch, or they don't comment on it particularly. But they say, from our analysis of replica symmetry breaking and metastable states, up to, in some region above this phase transition, there must be glassiness. Probably that will play some role on the dynamics, etc. But all this, we will comment on it, how much we actually know and how much we don't know. At that time, also people were interested in algorithms. Obviously, in machine learning, the biggest question is not what is the best error, but can we actually get the error algorithmically? So there is, this paper is maybe less well known, but it's very remarkable, by Manfred Opper and Ole Winter, where they actually write and use the Thales-Anderson-Palmer equations as an algorithm to compute this optimal generalization error in a perceptron with this time spherical weights. And here there is their picture, so it's a pretty good fit, although their size is 50 spins. So I never understood how in these like 30 years old paper with 50 spins they were able to get such good fits. I mean, okay, but we will, but it's a good fit. But they say that they conjecture that this approach is exact in the thermodynamical limit, which is not true for the binary spins, as we will say. And also a caveat is that the DAP equations really do not converge in this case for large n, as is somehow the well-known problem with DAP equations. So keep that also in mind. And maybe, you know, in my series of papers that I'm showing, maybe this one, that one is not on a perceptron problem, it's on a different problem. But it's a paper that somehow started to get a good notion of that there is something interesting going on that is not necessarily that some algorithmic hardness related to a first order phase transition that is maybe not necessarily due to glassiness, because from the static point of view, the model studied here is just the ordinary ferromagnet with the first order phase transition, yet the dynamics that is studied here never finds that ferromagnet. So this is just my personal selection from a huge body of literature that is somehow nicely summarized. These would be 2 reviews and 1 book that, again, it's a selection, so that's just my personal, I like those. Then, interestingly, for instance, when I was doing my PhD, there was not so much activity in statistical physics and artificial neural networks. It somehow faded. But of course, with the come up of these deep neural networks and everybody being excited about it, we are also back excited about that. But it's not that nothing happened in the meantime. In the meantime, in the past, say, 10, 20 years, there was immense interest in the results of the, say, replica methods in other fields, such as statistics and signal processing and information theory and probability theory. And if I should pick one paper from that period, it would probably be this one by David Donohoe and Ariane Maleki and Andrea Montanari on message passing for compress sensing, that, just the number of sites. These are not complex network people, so these are serious people that are citing this paper. But you see that it has a lot of impact, but not so much in physics. I would think that very, very little of these over 1,000 citations are in physics. These are really people in statistics, in signal processing, in machine learning, in probability, in math, etc. So with all that, what were the open questions that remained, say, 15 years ago? So let me list 4 of them. So this formula from the replica method that these old papers got for this generalization error, which is the main object that interests us here, if it is correct, can we prove it mathematically? It's a good question. Now, if it is correct, can it be reachable with a tractable algorithm? These stuff don't really converge, and the Monte Carlo we cannot really, we never know how it converges, etc. Okay, and what if the activation function is not a sign, but something else, for instance, the rectified linear unit that is popular in machine learning, or some generic other nonlinearity? Can we somehow put that generically in the formulas, not to have to write a new paper every time we change the activation function? And what if the weights were different, we had different constraints? They don't need to be spherical or binary, they can be sparse or any other distribution. So can we write a formula that takes that into account in some generic form? So this talk will answer all 4 of those. And let's start with the last 2. So how do we do for a different activation function and for a different constraint on the vector? So let's generalize this perceptron model. And let's introduce something that is very similar, called the generalized linear regression. So generalized linear regression is, an approach or model that is very common in say signal processing or statistics. It's as before, we have a matrix that represents the data set, and this time we have a function phi that for the perceptron would be the sign, but now it can be any function and it can depend on some noise parameter, etc. That generates some labels, but it doesn't have to be labels. These can also be real numbers in regression, etc. And the x has some constraint on it. So before, for instance, we said these are plus minus 1, but it can be any other constraint on a prior on the x. And the goal is to find the x such that this is satisfied as closely as possible. And if you state a problem generically like that, There are many problems in science that can be reduced to this setting, such as compressed sensing and reconstruction, computed tomography and NMR, and problems in phase retrieval and lasso and superposition codes, etc. And the problem that Imre was talking about yesterday and the perceptron Giorgio will talk about tomorrow, all that can be stated in this. But so far I didn't say anything. This is just a definition, right? This is just to say that indeed this generalized linear model, that's something used in science is pretty much everywhere. But now to do some statistical physics of it, we need to be more specific. We cannot take F generic. The matrix cannot be generic. So here we do the same thing as Derrida and Gardner did. We take this matrix that collects the data, the pictures or the patterns, if you were. We take it to have random IID elements. It has certain size, still the same, m times n. There's the number of spins, this is the number of patterns. In regression, this is the dimension, and this is the number of samples. And then we get this teacher-student scenario. So the teacher generates x star, generates f, and with those, and knowing this function phi generates y. And then the goal of the student is the student gets f and y, and it also gets the distribution px, and it also gets this function phi. The only thing she does not get is the x star. Okay, so the goal is, as before, to infer the x star, and in such a way that if a new row of f arrives, a generalization is possible. So now, Imre yesterday said that we do these assumptions for simplicity. We can also call the authority of Derrida and say we just do it the same as he did, and Gardner. This is where, when I talk to mathematicians or computer scientists, this is where the clash of the cultures comes. So to them, I need to show a slide like that. Why are we taking IID matrix F and IID X star? This doesn't make sense, right? The picture of a cat is not IID white noise. The picture of a dog neither. No data that come in statistics for which you do regression is an IID white noise. Nevertheless, this is, I insist that this model is interesting to study for at least these 4 reasons. So first of all, we can write a tractable theory. So in statistics, they also, of course, have theory, but it works in different regimes. If we want to include constants, such as the phase diagrams we are getting from the replica method, basically there is no math that is able to do that at this point, except the math proving the replica theory. Sometimes this setting is realistic. So for instance, here in these applications, like the compressed sensing, the superposition error correcting codes, or this code division multiple access problem, whatever those are, it is actually realistic that the matrix that corresponds to the data set is a random matrix. Not always, sometimes. Another reason would be because the behavior of this model is interesting. When we actually look what it does, it has phase transitions, and from the point of view of algorithms, what's going on is not clear. So as long as it's interesting, I personally like to study it. And a reason that somehow speaks often to the mathematicians that it's challenging. We have a prediction for what the formula for instance, the generalization error is in those papers. Great mathematicians looked into that problem, and we still don't have a result before this talk, say. Okay. So that's definitely challenging that's a good reason for me and also many other people. Okay, so how do we attack this problem? So this teacher-student scenario for the perceptron problem, if we want to calculate the optimal generalization error, and we don't care about the algorithm or about the time for which the algorithm will be running, we know what to do. Okay, we just need to take a book of Bayesian inference, go to page 30 or something like that, and we will learn that what we need to do is the following. We need to write the posterior distribution of what is the x, the unknown, given the known, so the y, the labels, and the data f, and that will just, by definition of the model, be given by a product of the prior terms and by a product of these likelihood terms. This p out is a probability distribution that a given label was created given the product of that x and f, so related to the previous function phi by this simple formula. And then the setting is the same. The y was generated using this x star, and the goal is to estimate the x star back from f and y, and if we get a new row of f to predict the new label, Okay? And the way to do that, we know what that is. We have to compute the posterior mean of xi in that probability distribution. So in a physics term, we need to compute the local magnetization of that corresponding Hamiltonian, if you want. So that's if we want to estimate optimally the x star. Precisely said, if you want to minimize the mean square error between the estimator and the true. And for the bias optimal generalization error, what we need to do, we need to take the new row of that matrix, plug it into our function, and multiply it by an x that is taken from the posterior and average over the posterior. And that's the prediction that will again minimize the mean square error between the true and our prediction. Okay, so in principle we know what to do, so that's good. And just a note that, that doing it this way, there is no overfitting. This is really the optimal thing. We know the model, so no such concept is bothering us here. And no other procedure can be better. The trouble is that this is not a tractable procedure. Okay, but we have the replica method that gives us the answer. But let's go to the first open question. Can we prove that answer mathematically? So the answer is yes, we can. But maybe, in front of the mathematicians, I must talk why IIDF is a good model. But maybe in front of a physics audience, why the rigor after all? I'm sure there are some among you that will say, but we understood these things 30 years ago. Why should we trying to prove that? That's useless. I mean, just should do something else, right? No, that's, let me spend a slide on it. I insist that without having, if we have a prediction that we really think is an exact in a certain limit for a certain well-defined model, then proving it is really contributing something. Because without having the proof where really every epsilon, everything works, we really don't get as deep understanding of the range of validity of the result as we can possibly get if we actually manage to prove it. And so really going beyond physical analogies, beyond what is reasonable because some disordered magnet behaves in the same way. And of course, because it generates new math that then is applicable to other problems about which maybe physicists would not think about because there are so many different problems that we just can't work on all of them. And the third point is that because it simply is a standard in mathematics, computer science, and statistics. If you want to publish in conferences and journals of this field, they can be open-minded, but it's better if you have the proof. So here it is. There's the replica free entropy, just the sign is different. The replica symmetric one, written in it for this teacher-student generalized linear model. So if you want to think back about the binary perceptron, because that's what you're familiar with, what you need to do, the p of x is just binary. So whenever in these integrals there is x or x0 that appears, and you are averaging over its distribution, is simply that this p of x are Ising spins. Okay? And the other thing is this p out function that was the sign before. So this means that the probability that you generated y that is 1 if this argument is positive, and in 0 if this argument is negative, and vice versa for -1. So that's where the activation function and the prior on the x appears in this p out and px. But otherwise, you see, this is a generic formula. It's a plug and go. You can take any activation, any prior, you put it in. For some reasonable ones, you simplify some of these integrals. And then this is the replica symmetric formula. I realize that even those that are familiar with the replica symmetric formula for the perceptron will probably not recognize this formula, because it's written with a particular goal to which I'm coming. But nevertheless, that's the formula, and you take infimum with respect to this parameter and supremum with respect to this parameter, and that gives you a number. And the theorem is that indeed, if you define the free entropy in this way, in the thermodynamic limit, then this quantity concentrates around this number. That's the theorem. And okay, in physics, we know why free entropy is interesting. But when I'm giving this talk to the mathematicians, I say, this seems like a useless quantity. We are interested in the error. But in physics, we are not surprised that in order to compute the optimal estimation error, we are just needing to take the maximizer here and plug it into this formula. And that's the optimal estimation error. And if we want the optimal generalization error, we take the maximizer and we plug it into this formula. And that's the optimal generalization error. I don't really know if this has a physical analog. This is somewhat a formula that is not so intuitive. So I guess you just have to believe me that that's the optimal generalization error. So now let's go to the form in which I wrote this free energy. And that also gives us, that brings us to the proof idea. So if you really don't care about the math, just take break for 4 slides or something like that. And then we are coming back to something without that. So why did I write this formula in this form? That's actually for a very good reason. Because if you stare at these integrals phi px and phi p out, they are actually free entropies of not high-dimensional problem with complicated interactions and n spins where n goes to infinity. These actually are free entropies. Here I wrote scalar, but I guess for physicists I should have written of a single spin problem. So these are free entropies of single spin problem, 2 different problems. This one would be where we generate certain y prime with some x star that is chosen from this distribution px. But this time x star is not a vector, this time it's just a real number. And this is just some parameter m star that I need because it will then appear in the formula, and a noise that is just Gaussian noise. So I generate y star, and then I need to compute the free entropy of how to estimate x star back from y star. Right? So I generate a scalar random variable, I multiply it by a constant, I add a noise, and then from the result I want to find it back. So everybody who just understands basics of Bayesian probability can write the integral that corresponds to that free entropy, and that's precisely that formula. And the other one is a different. It's not related to the prior, but it's related to the activation function. And the variable we are estimating here is the z star, and this time I shift it, I multiply it by a constant, and then I send it through this channel. And what I observe is this y tilde, and then the goal is to get z star back from y tilde. But again, it's a 1-spin problem, so everybody can write the corresponding integral to the free entropy, and that will be that formula. So that's interesting to realize that actually the replica formula has this modular structure that is basically 1 denoising problem plus alpha times a different denoising problem. Remember, alpha, there's always the ratio between number of samples and the dimension, minus just the combination of these 2 constants. And that's also, this realization stands at the beginning of the proof, because then what we do is we use the good old Gura-Toninelli interpolation between the original system and n plus n of the scalar problems of type 1 and m of the scalar problems of type 2. Then we write a Hamiltonian that is combining these 2 in such a way that it depends on this parameter t, which is a kind of interpolation time, if you want. If this parameter t is 0, we are back at the original problem. This is, it's only the original problem. All the other terms are 0. And if t is 1, the original problem doesn't matter. And we are just ended up with m plus n independent spins with some particular probabilities on them. So with that in mind, we realize immediately that at t equal 1, we know what the free entropy is. At t equals 0, that's what we want to get. So if ever we are able to show that as t is changing, this free entropy is not changing, we are done. But of course, that's the core of the proof. That's where the 40 pages of the paper go. And I will not be going through the details of that. But just one thing to say, for this to work, 2 things to say actually. The interpolation path that we are taking here is actually some parameter that depends on the interpolation parameter, which is not the canonical interpolation. In the canonical interpolation, this would just be a constant here. And in order for the proof to work, what we need to do is to adapt the path so that the remainder, that means the difference between these 2 terms on the way, vanishes. So there is some differential equation on the way that tells us how to adapt this m of t so that this happens. And as the proof goes, on several different places, we need this property that is called the Nishimori condition, that is simply saying that under expectations over the posterior, the ground truth X star can be replaced by a randomly drawn sample from the posterior. And that is a property that in spin glasses is true on the Nishimori line, but in Bayesian inference is true by the definition or by the meaning of the Bayesian theorem itself. So we call it Nishimori conditions, and the mathematicians laugh at us. They say that's a trivial application of the Bayes theorem. But then they do integration by parts and call it the Stein lemma, so then we laugh at them. So okay, everybody has it. So I will not say more about that, just to say that it relies, this work relies on, on the interpolation by Guerra-Toninelli, and somehow really got inspired that something like that is possible by reading this pretty much forgotten paper by Corrada and Macris from some 10 years ago, and the series of works by Montanari, where he also, in different contexts, has proofs of the replica formula, but always in an absence of the first order phase transition. So the first order phase transitions complicates things, but with this adaptive interpolation method, we can go through that. And that's a series of papers by, me and collaborators from the past 2 years, where we were somehow having fun showing those for a bunch of problems, SK-like or on sparse graphs, or for this linear regression or the generalized linear regression. Okay, so now the math stopped. So for those who drifted away, wake up, because now I showed you, okay, so physics prediction led to some new math. And this is nice, okay? Makes us feel good. But people often ask me, can we go back? Is there actually some path back from the math to physics? And in this case, it's one example that I know where there is. And it comes when you actually ask, what is the optimal error reachable with an efficient algorithm? And we didn't have such an algorithm in physics. And it came from, that's one of the papers that I cited before, this one by Donoho, Malek, and Montanari. It's a version of the message passing algorithms. And this is this generalization by Sandeep Rangan, who is in information theory. So you see, these are not older than 10 years paper and are quite well known. So this is the algorithm, the pseudocode of the algorithm. Okay, it will not tell you much. It's an iterative algorithm. It's not hard to implement. It runs in time that is just n squared, just as small as you need just to read your matrix. So it cannot possibly be better. And it iterates the estimator of your magnetizations and their variance, because spins are not generally ±1, so the variance is not in general trivial. And it also gives you an expression for this bias optimal prediction, which is interesting, right? You would think, oh, integrating over the posterior, that must be a hard thing to do. No, this algorithm gives it to you. It's just a simple expression. Once you get a fixed point, you plug it in. So what's the story of this algorithm? Because I show you the equations, you didn't even have time to read it, or probably they were too small. The story is the following. It's really interesting. It's really closely related to the Thouless-Anderson-Palmer equations that for the perceptron model were written by Mark Mezar in '89. But at that time, the focus was not to use them as an algorithm. It was to derive the replica method without having to use the replicas, because everybody was about dubitative about how correct that is. But the thing is that I told you, right, with this paper of Opper and collaborator, and with many other papers that appeared in the field, that these type equations never converge. Even in the replica symmetric phase, these are, you would like to use them for something, but it usually doesn't work. And, it's trivial reason, for a trivial reason. These type equations, as people were using them for 40 years, simply had wrong iteration time indices. So this is for the SK model, okay? So this is an equation that will be familiar to many of you, I think. But note that whereas here is magnetization at time t, and here it is at time t-1, and here it is at time -1, here it's time -2. You say, okay, that's a little trivial change, right? That cannot change really anything. By the way, Boldhausen kind of recently that realized that. And that actually changes everything. And just to illustrate how much that changes everything, some 3 years ago, I received this mail from Giorgio Parisi saying, "Ma come è possibile che a matematico ci abbia sorpassato?" So how is it possible that we were passed by mathematicians? Look at this paper of Bolthausen and change the time index from k to k-1, and now it converges. I can't believe it. I just read it in Lenka's thesis, and I can't believe it. So, okay, by the authority of Giorgio Parisi, this should somehow persuade you that this is not a trivial thing to change this time index from t to t-1 or from t-1 to t-2. Suddenly things work. And suddenly this algorithm behaves exactly as the replica theory predicts. And even strikingly, surprisingly, so we will be getting to that. So what we can get with this algorithm, where we simply change the time index from t-1 to t-2, is what is called state evolution in this more recent literature. That's really Andrea Montanari that is the leading force in proving these kind of things rigorously with his group. So what is this about? So I showed you this algorithm that you probably don't understand if you never saw it before. But there was in it this quantity that was estimating the magnetization that we are interested in. So we define this order parameter that is the correlation between the ground truth and the estimator. Okay, that's a natural thing to do. And that the state evolution tells you that at time, as you iterated the algorithm t times, the value of this order parameter follows this equation. Is just a derivative of this free entropy that appeared in the replica symmetric formula. And for the other parameter is the derivative of the other free entropy. So you see from this that this is just doing a gradient ascent in the replica free energy, nothing else. So in a sense, we somehow knew that. But for the type equations as they were implemented before, that was not true because the time indices were wrong. So if you correct them, it rigorously, in the large n limit, does that. And note that this is quite remarkable. In the landscape of algorithms that people use in statistics or in Bayesian inference, a lot of people use Monte Carlo, call it Gibbs sampling, and a lot of people use naive mean field method and call it variational bias, and or our variants on the Langevin dynamics. But for all these, we don't have any analysis that would trace what the algorithm is doing time step to time step. Maybe with the exception of the spherical p-spin and the Langevin dynamics, where we know how to solve the dynamics exactly, but still it comes with these like integral differential equations that are infinitely more complicated than this. This is just an equation on one scalar parameter. And one more thing, and that's that this algorithm follows the gradient of the replica symmetric free entropy, even when the teacher is not the student, even in situations where physically there is replica symmetry breaking in the system. This algorithm doesn't care about it. It follows the state evolution even when it doesn't converge. It doesn't care about its own convergence. It cannot converge, and it actually does, exactly below the AT line, and that's exactly what Bolthausen proved in his paper. But even when it does not converge, it follows the gradient in the replica symmetric free entropy. So in a sense, David, your wrong replica symmetric solution of the SK model is maybe wrong for the physics, but it describes exactly the behavior of this algorithm that now is used by thousands of people. So after all, it's not so bad. And so just the bottom line, to connect now to the replica theory, right? Because now I really like this algorithm, as you might notice. So just to connect with the replica theory, what is actually going on, and to connect to the picture, to this unphysical branch that Georgie was telling us about. So what's going on? All is in this free entropy. It's a function of one parameter, and it can either have one maxima, in that case, both the bias optimal error and the behavior of the algorithm is given by that one maxima, or it can have multiple maxima. And in that case, the larger maxima is giving the optimal error. And the maxima that is for the smallest m, which is the correlation with the ground truth, because the algorithm is starting without any correlation, it's starting to ascend from m equals 0. So it gets stuck at the first maxima. So that's the maxima that describes the behavior of the algorithm. So as long as we can plot this function, we have everything. So let's look at how this function looks like for the teacher-student binary perceptron. For this case that, you know, many people in the audience know really well about, and even before I knew, you know, even what an integral is, they knew about it. So the binary perceptron, how it looks like. So again, you know, for those, so that's when the activation is a sign, and when this x is taken as a Ising variables. And this is just the Georgi picture. The y, so the x-axis is the alpha. It's the number of samples divided by the dimension. That's common in the two pictures. The y picture, I have the generalization error in terms of the mean square error, and Georgi plots the angle between the two vectors. So it's not quite the same thing, okay? But there is a trivial relation between one and the other. And so you see here the red. That's a result of where is the global maximum of the replica-free entropy. So that's exactly the same curve for Georgi as for me. He had like 5 here instead of 9, but okay, this is a double integral, so at that time it was maybe not so easy to compute it up to 4 digits. But then this branch that he called unphysical, it's not unphysical, it actually gives us the behavior of the algorithm. So that's the green line. That's the unphysical branch cut it when it jumps to 0. And the black points, that's the approximate message passing, not run on 50 spins. It just, I never can get a good agreement on 50 spins. That's why I was saying I don't understand how at the time it was so good. This is on 10,000 spins, and you see, you know, there are some fluctuations, but they are barely visible on the scale of this image. And just for interest, comparing to the blue points, so if you take a good student in data science and you sit her down with scikit-learn for, say, an hour and give her this problem of classification, that's some black box algorithm, logistic regression of support vector machine, that will give you a line like that. So you see, it's not quite following, it doesn't capture the phase transition. Okay, so GAMP is optimal out of the hard phase. So this is saying that this algorithm is asymptotically giving us the optimal error everywhere, except the region of parameters here. And in a sense, it's a redemption of this unphysical branch and of this unphysical replica symmetric solution. It's perfectly meaningful if you care about what this algorithm does. So now it gets quite interesting, actually, because remember this picture I showed you from the Sompolinsky-Tishby paper, where they were saying, oh, but after this phase transition, there is a glassy phase. So Monte Carlo will slow down, etc., etc. The approximate message passing doesn't care about the glassy phase. I told you that it follows its state evolution no matter what. So it follows this green line no matter what. But that's kind of interesting. So we were actually thinking kind of recently with Pierfrancesco and my postdoc Fabrizio and Silvio, couldn't we take the glassiness into account and improve over the approximate message passing? Sounds a good idea. Well, at least it did to us. So we did it. And then realized that actually no, we can write a version of the algorithm that takes the glassiness into account. We're quite happy about that. But when we analyze it, we realize that the best among all those algorithms is the original one that doesn't take the glassiness into account. So, okay, I don't understand physically why that is true, but it definitely brings up a question, you know, can algorithms beat GAMP? On which I think that no. Can it at least match GAMP? That's a good question. We don't know what would Monte Carlo still do in this example, or Langevin dynamics. Would it be as good as this algorithm or not? That's an open question. This somehow brings us to the fundamental nature of what I call this hard phase. Because I showed you one algorithm that doesn't work in some region of parameters, but there are thousands of others. You should tell me some other will work there, right? This is hard, but you should not call it hard, it's too pretentious. So I don't think it's so pretentious, actually. So first of all, okay, so this hard phase is always associated with the first order phase transition. It's a spinodal region of a first order phase transition. It has been identified in a bunch of problems, on most of which we worked in the past 10 years or so. Okay. And the conjecture that in all these problems, the approximate message passing achieves the lowest error among all polynomial algorithms as long as the worst case of these problems is NP complete, seems to stand. And there are some pretty good evidences towards that. One of them is, for instance, in this Despande and Montanari paper, where they really prove that this algorithm is optimal within a big class of algorithms. It will not be easy to prove that it is optimal among all polynomials. That would be showing that P is not NP. That would be a bit pretentious. But within well-defined classes of algorithms, this is definitely something that we can hope for. So that's a question on which I'm thinking a lot, like in recent years, basically, for what classes of algorithms can we give some lower bounds on computational complexity. So just to say, maybe many of you know about this paper. It's quite well known in the community, right? That's one. Somehow these ideas that phase transitions have something to do with computational complexity is in the community for a long time. And this is definitely one of the influential papers in that respect. And here, for instance, they are saying, depending on the input parameters, the computing time may grow exponentially or polynomially with problem size. In the former case, we observe a discontinuous transition, whereas in the later, a continuous second-order transition is found. So that somehow sounds similar to what I'm saying, right? But note that that's not, it's not similar in the sense that this paper was talking about constraint satisfaction problems, such as case satisfiability and optimization problems, where you have a landscape and you try to find the minimum. For these type of problems, we actually do not have thresholds that would be phase transitions and that would, where the conjecture that this is in some sense a universal threshold where this conjecture would hold or stand. Maybe some people believe some, but definitely there is no agreement. Whereas for these inference problems, where we planted some X star and now we are wanting to find it back, the spinol of this first order phase transition, that really is a conjecture that so far stands. There is no even a hint by numerical simulations, that wouldn't be in some regime where finite size effect can be like crazily large, that would really speak against this conjecture. So it's kind of interesting. After all, this is true, but in a little bit different context. At least that's what I would say currently. Where am I in terms of time? I'm done? -1. Okay, good. So then I stop here. So you can ask me about these later. And there is some, maybe one word on the ongoing work, because of course all these assumptions that we did on the data being random and the prior being separable, these are of course things we want to go beyond, and that's what we, that's what we are working on, to basically talk of models that are more realistic than that. So I think Mark will mention some of that tomorrow. And these non-separable priors, basically priors that come from a different graphical model and then lead to multi-layer neural networks. That's somehow the things that amuse us these days. And with this, just maybe I will end up with this one, which is somehow summarizing the things that I think are new and interesting with respect to 27 years ago or so. Okay, over my time. Thank you.
Lenka? Question?
Can I ask you a question about your initial examples of cats and dogs? We find it very easy to tell whether a picture represents a cat and a dog. And I think we probably do it by focusing. This is a hypothesis. We focus on the nose, and we have a big black dot in what we might call the nose area, means it's a dog. Now, can you, with these algorithms, show that when you've got a successful algorithm, it is working in a way which mimics, say, what I just said?
Yeah, so that's of course as large question and field in machine learning as the whole statistical physics or say disordered system physics would be in physics, right? So a lot of people in machine learning are asking the question on what's the interpretability of what these deep neural networks are learning. And it's a widely open question in the sense that, this idea that you have, we focus on the nose, and so can the algorithms do it this way? However reasonable it seems pretty like it's not, if you try to focus on that, and surely people did say 20 years ago, and they never came up with anything that would actually work well. So these algorithms that actually do work well, on the other hand, we don't really understand what they understood and what in the data they are focusing on. So many people study that. I don't really have that's not really my field. I don't really have like the best answer, but definitely there are like dozens and dozens of paper on that question. That's important question because if we want to do science with this, it's not only important to have like good generalization error at the end. We also want to understand what the algorithm understood about the system. And this is a big gap, in a sense, in the current somehow state of art.
I would like to know what is the status of the binary perceptron. Is it fully solved now, or
For the capacity, I would think you're interested. So because here this was about the teacher-student,
yes,
so that's simpler. For the binary.
You mentioned the 1.249. So what is the status? This is an exact result, or is it?
Yes.
we
So
need to do some approximation?
this is the 1.245. That's a numerically evaluated the integral of the replica method. So if you really wanted to make it rigorous, you would have to prove that that's indeed the number to which this integral goes. But the fact that the error is given by that integral, that's a theorem in the teacher-student case. Okay. In the storage capacity case, that's a different question. So I believe that the result of in the Kraut-Meza paper is correct. Now for the binary perceptron with the sine function, this is not yet established. I actually talked rather recently with Nike Sun from Berkeley, who is one of the author of the K-satisfiability of the proof of the K-sat threshold. So she's working on that, and it seems like she has the lower bound, but not the upper bound, which is kind of interesting because usually it's the other way around. So she knows how to tweak the second moment method to show the lower bound, that the replica prediction is tight. But by tweaking the second moment, she forgets some solutions, so one cannot do the same thing for the upper bound, so the upper bound still seems open. An interesting realization is that actually if you slightly change the activation function, you take not sine of patterns times a weight, but you take sine of absolute value of pattern times a weight minus a constant, not to make it completely trivial. So you symmetrize it. You see, all that you put in is symmetry in the weights. So that somehow magically simplifies things in terms of the moment method. And so for that case, there is a second moment and a first moment bounds that match, that show that the replica prediction is correct. Again, the replica prediction where the entropy goes to 0, okay? And physically, symmetrizing this activation function this way should not change much, really, right? I mean, it's just because we studied the sign because that was somehow first that came to mind. But from the point of view of phase diagram, like I can't really see anything in the physics that should change between the sign and the symmetrized sign. So that's the status of the storage capacity.
So if there are no other questions, thank you very much again.